Well, hello. I'm Jim Rosenthal, and for whatever reason have decided to go ahead and produce a series of videos of the PowerPoints for my text. So we're getting ready to go, and we're starting on Chapter 1. And just begin with the mention of evidence-based practice, that we want social work to be based on the best scientific knowledge available, rather than perhaps simply on what feels good, say. We don't want to take the human side out of social work, but we want to ground it in science. Much of Chapter 1 is definition after definition, so you've just got to kind of bear with me, and here we'll go. So a statistic is a numerical summary of data. So for instance, if the students in your class are on average 5'4" tall, then 5'4" summarizes data for your class as and therefore is a statistic. And here are a couple of other statistics. So for instance, 23% of social workers wear red suspenders. If that is so, then that 23% is a statistic. So here's the definition of social work. And importantly, social work concerns itself at multiple intervention levels. Here's a definition of statistics, the science of making effective use of numerical data. The gist of the matter is that as social workers, we need to find out what works and what doesn't work, and statistics can help us do that. There are two approaches, quantitative and qualitative, to research in social work and social science. When you think of research, you're thinking almost assuredly of quantitative methods. Basically, survey, experiment, assigning numbers to categories. Each person in a survey will respond to the very same questions. Qualitative research, on the other hand, emphasizes in-depth understanding. And the notion with qualitative research is that each person's response is going to be different, and open-ended, and reflect their particular perspective. I just mentioned that ethnography, anthropological research in cultural settings is an example of a qualitative research method. Many social work studies, or at least some, combine quantitative and qualitative methods. Each has complementary advantages, which can be discussed in your research methods course. So here we have some more definitions. Data, the observations gathered. Cases are your units of measure, so that if you distribute your survey to the different people in your class, then each person is a different case in your data. I like to define variables as the ingredients of data. So some examples of variables in a data set might be, if it's a class survey perhaps, gender, height. You may be asking questions about self-esteem. GPA is another possible variable. So the key notion about variable, I mean, it's there in the name. For something to be a variable, it's going to take on different values. So for instance, a political party takes on different values. Democratic, Republican, Communist, Libertarian. Those are examples of the different values that the variable political party might take on. Gender can take on the values female and male. Eye color, the values for eye color would be the various colors of eyes. Blue, brown, green, and the like. Social work research has two different categories, so to speak, of variables. So we have quantitative variables. Quantitative variables have numeric values. So, for instance, height, as commonly measured, has numeric values. For instance, 5'7½". Height is an example of a numeric variable or a quantitative variable. On the other hand, gender, female or male, does not have numeric values. Therefore, it's an example of a qualitative variable. So qualitative variables have non-numeric values. Particular categorical or qualitative, those are synonyms. A particular type of categorical variable is a dichotomous variable, sometimes called a binary variable. And that is a categorical variable with exactly two categories. So gender, as we've defined it here, is a categorical variable, and indeed it is a dichotomous variable as well. And here are, as promised, still more definitions. A population can be defined as all of the objects that possess a specified set of characteristics. On the other hand, a sample is defined as some of the objects that possess a specified set of characteristics. There are two basic types or divisions of samples in social science. There are random samples and non-random samples. Random sampling and probability sampling are synonyms, and in random sampling, methods of chance are used to choose the sample. As for instance, if the names of 10 people in your class are put in a hat, and the hat is shaken, and then some names are selected from that hat, that's an example of random sampling. And I guess I mean to say all of the names would go into the hat, all of the names, the full population, and then if 10 are selected at random, that sample is an example of a random sample. Non-probability sampling, which is to say non-random sampling, is in essence the opposite of probability or random sampling. So in a non-random sample, methods of chance are not used. I mean, that's how the definition is. So for instance, if all of the students sitting in the front row in your class are picked to be in some study, then those students were not picked using a method of chance, but were picked instead because they sat in the front row, and that would be an example of a non-probability, which is to say a non-random sample. I mentioned earlier that a statistic is a numerical summary of data. There are two branches of statistics. Descriptive statistics describe the study sample. Inferential statistics are used to draw conclusions about a population based on a random sample selected from that population. So let's look at some examples of descriptive and then inferential statistics. So if a professor handed out a survey in class, collected that, and then analyzed that data, and for instance reported 80% of students in my social work class are female, the professor is not trying to draw any conclusions about any group beyond or wider than the social work class. Conclusions are limited to the class per se. So that is an example of descriptive statistics. Now, inferential statistics, and an exception will be presented in the middle of the course, but for now, inferential statistics require that the sample be a random sample. So if one sample is not a random sample, then inferential statistics is not a valid process. So if a professor takes a random sample of students at her university, and let's say 46% in her sample support a change in immigration policy, she might report something like, we can be 95% confident that the percentage of students in the university that supports the change is between 40% and 52%. Now, for now, don't concern yourself with how we got the 40 and the 52. I mean, in essence, I sort of picked those percentages out of the air. But the key idea is that the conclusion that's being drawn is being drawn about the population from which the random sample was selected. And that's the distinguishing characteristic of inferential statistics. So we've just seen that one division of statistics is descriptive versus univariate, and another would be univariate versus bivariate versus multivariate. Univariate statistics summarize a single variable. So if we say 72% of students are women, we're only talking about one variable, that being, in essence, gender, female versus male. Bivariate statistics summarize relationship between two variables. Relationship can be defined as the degree to which values observed for one variable go with those observed for another. A synonym for relationship is association. We may also say that associated and related are synonyms. So relationship captures a notion almost of going together. For instance, taller height and being male tend to go together. Or one could look from the opposite perspective and say being short and female tend to go together. So we have a pattern that certain values of one variable tend more often to go with particular values of the other variable. So male tends to go with tall, female tends to go with short, and that's the core idea behind relationship. So we can say then that gender and height are related. And it's the pattern, the trend, establishes relationship. We don't need to have, so to speak, perfect relationship. It need not be the case that every man be taller than every woman, but rather that on average, men are taller. Here's a second example of two variables that are related. Age and how much one's bones ache upon waking up are related. In essence, the older the age, the greater the tendency to have aches and pains in one's bones. And all older people don't have aches and pains. All younger ones are not free from aches and pains, but older people are more likely than our younger to have aches and pains, and so therefore we've got relationship. Two variables, and I'm going to say in a random sample, can be related simply due to the luck of the draw, and this is a very important concept for inferential statistics, which we look at predominantly in the second half of this course. So, suppose that in your university it is the case that equal percentages of women and men are vegetarians, say 10.7% of each gender. Therefore, in the population, which is to say, among all students at the university, gender and vegetarianism are unrelated. Now, the absence of association in a population does not guarantee the same in a random sample selected from that population. So one could have absence of association in a population, but due to the luck of the draw, one could indeed have relationship in the random sample selected from that population. So we have equal percentages of women and men, say, in the population, yet when we draw random samples, due to the luck of the draw, we find differing percentages of women and men in our sample. So even though we have no relationship in the population due to chance, luck of the draw, we have relationship in our random sample. Indeed, it's quite common to face this conundrum that the social work researcher never has data on the full population, or at least rarely has such, but instead is oftentimes working with random samples. So the researcher sees relationship in the random samples, yet the fact of that relationship doesn't let her conclude assuredly that there's relationship in the population. Basically, determining whether relationships in samples are likely to be due simply to luck or chance, that is indeed the key focus of inferential statistics. And indeed, I mean, the second half of the course is devoted to inferential statistics. The key application of inferential statistics is the statistical significance test, and significance tests examine whether results, which is to say relationships that we find in random samples, are plausibly due simply to the luck of the draw. But I mean, just to finish up from that last slide, I mean, it's often the case that one group gets one intervention, a second group gets another intervention. There's a difference in performance in those two groups, and it's possible that that difference in performance reflects not a real difference in the effectiveness of the two interventions, but instead simply the luck of the draw of the random samples, or the random assignment of persons to intervention A versus intervention B. And so looking at whether luck is a plausible explanation is a big, big part of, I mean, that's the central part of inferential statistics, and that's a big, big part of statistical analysis. Well, we've looked at univariate stats, and we've looked at bivariate statistics. I mean, bivariate statistics is, in essence, the examination of relationships between two variables. Sometimes statistics is indeed multivariate statistics, which is to say that three or more variables are involved at the same time. A key use of multivariate statistics is to begin to examine the question of whether a given relationship is a causal relationship. Let's look at an example of a relationship that is not a causal relationship. Ice cream consumption per person and the crime rate in New York are positively related, which is to say that the more ice cream that is consumed on any given day, the greater is the predicted crime on that day. So as ice cream consumption goes up, so does crime. The notion is this relationship a causal one? If indeed it were a causal relationship, then somehow ice cream consumption would be causing crime, or perhaps it's the other way around. Perhaps crime causes ice cream consumption. This relationship almost assuredly is not a causal one, but rather this relationship is due to a confounding variable. A confounding variable is a variable that can bring about a relationship between two other variables. So what's the confounding variable in our ice cream crime example? Well, you've probably guessed that it's temperature, which is to say that on warm days, people eat more ice cream and people commit more crimes. On the other hand, on cold days, people eat less ice cream and tend to commit fewer crimes. So the big idea is that third variables, which is to say confounding variables, can bring about relationships between two other variables. So this is another big question that often comes up in social work research. We find relationship between variables, and we then try to discern, is that relationship a causal one, or on the other hand, might it be due to a confounding variable? We're shifting back to a sort of a definition mode again. An independent variable is a variable that affects another variable. On the other hand, the dependent variable is the affected variable. So if intervention X reduces depression, then we would say that intervention X is the independent variable, the one doing the causing, and that depression is the dependent variable, the one that is affected. In social work research, the intervention, sometimes called the treatment or the treatment stimulus, the intervention is the thing that is done to the study participant. So an intervention might be a particular type of behavior modification, it might be a marital therapy intervention, it might be parenting skills training. So we're working here now in the realm of different kinds of research studies, and the term assignment is an important one. Assignment is the method used to assign participants to groups, which is to say to different interventions. Now there are in essence two types of assignments, basically speaking. Random assignment is the use of methods of chance to assign participants to groups. Importantly, random assignment eliminates the problem of confounding variables. In other words, if a researcher conducts a study with random assignment and a difference emerges such that outcomes are better in one intervention than in the other, then that relationship of one intervention to the better outcome and the other to the worse, that intervention cannot logically be due to confounding variables. So random assignment helps considerably in drawing causal conclusions by ruling out confounding variables. On the other hand, in other studies, assignment is non-random, which is to say perhaps kids are assigned to different types of foster care settings, not by chance, but rather by a social work staffing, which is to say based on their needs. Well, in studies that examine outcomes where assignment to groups, in this case, you know, the different types of foster care placements are the different groups. We can also say the different interventions. But if we don't have random assignment and then we see differential outcomes, it's very difficult to know whether those differential outcomes reflect the effects of treatment or instead those of confounding variables. Because perhaps, for instance, kids with less serious problems tend to go to one type of foster care and kids with more serious ones to another. Well, then if the first type of foster care yields better outcomes, it's logically difficult to unravel whether the less serious problems of the kids or the real treatment benefit, if any, of that type of foster care is responsible for the outcome. Well, we're shifting gears here, and most of the rest of Chapter 1 pertains to levels of measurement. And so there are 4 levels of measurement, which is to say variables can be measured at 4 key levels, and sort of ordered from lowest to highest. These are nominal, ordinal, interval, and ratio. Noir, the French term for night, to help you remember that order. As you go from a lower level up to the next higher one, you're gaining new and more precise information, and qualitatively different information. At the nominal level, one can classify values, but these values or categories cannot be ordered. So the idea is we can classify eye color into blue, brown, green, hazel, gray, etc. Yet these values can't be ordered. No value of eye color is higher or lower than is another. For instance, brown is not higher or lower than green. And similarly, we would say that gender is measured at the nominal level, and that's because neither gender, female or male, is higher or lower than is the other. At the ordinal level of measurement, one can classify and order values. For instance, questions that measure strength of agreement are at the ordinal level of measurement. So one can say that strongly agree is greater than agree, which is greater than disagree, which is greater than strongly disagree. So unlike at the nominal level of measurement, at the ordinal level, we can order values from low to high. I note quickly that rank orderings are ordinal level measure. So we could have all of the class stand in a row ordered from tallest to shortest, and that would give us a rank ordering. And those orderings do indeed follow an order. So for instance, we know that rank number 2 is taller than rank number 3 is taller than rank number 4, and so on. Moving up from the ordinal level to the interval level, at the interval level of measurement, we can order values and measure differences between values. What, for instance, is the distance between strongly agree and agree? Well, this question makes no sense, as these values are not numeric. What's the difference between 10 degrees and 5 degrees Fahrenheit? And here we can subtract meaningfully one value from another, which is to say we can measure differences, we can measure intervals. So 10 minus 5 equals 5. Being particular, when we reach the interval level of measurement, then the mathematical operation subtraction can be carried out and is valid. At the ratio level of measurement, we can measure distances and also calculate ratios. At ratio level, the 0 point on the measurement scale conveys the absence of what is being measured. Another way to say this same thing is to say that the 0 point on the measurement scale is a true 0. When the 0 point is a true 0, ratios make sense. So for instance, is 10 degrees Fahrenheit twice as hot as 5? The answer is no, it's not. And this is because, basically, 0 degrees Fahrenheit does not convey the absence of heat. So when the 0 point on the scale is not a true 0 point, ratios don't make sense. You can't divide 10 by 5 to pronounce that 10 degrees is twice as hot as 5. You can't do that at interval level. But you can do so at ratio level of measurement. So for instance, we can divide 10 pounds by 5 pounds. That is to say, we can form a ratio, and that ratio is 2. 10 pounds is twice as heavy as is 5 pounds. This is a valid ratio. And this demonstrates that weight is indeed at the ratio level of measurement. So ratio level variables are numeric, and then additionally, the 0 point is a true 0. At the ratio level of measurement, from a mathematical perspective, we can validly multiply and, for that matter, divide values in addition to subtract them. So subtraction and addition become possible at interval level, and multiplication and division are valid at the ratio level of measurement. So let's discuss levels of measurement just a little bit more. A variable's level of measurement is oftentimes very important in determining which statistical procedures can validly be used. Suppose, for instance, that a variable is measuring level of agreement with something, and that its values are strongly agree, agree, disagree, strongly disagree. Well, these are non-numeric values, so that, for instance, if we have a variable that's measured in this way, you could not formally and validly calculate an average, which is to say you couldn't add up all of the points and divide by the number of cases. You can't calculate an average because the values of the variable are non-numeric. But on the other hand, if we had a numeric variable, that is to say a variable in essence at interval or ratio level, then indeed we could calculate an average. A general rule is in most situations you should measure with the greatest possible precision, which is to say measure at the highest possible level, because that will open up additional possibilities for statistical analysis for you. A pragmatic point is that for variables at the interval and ratio levels of measurement, the same introductory statistical procedures are used for variables at both of these levels. So while I presented a clear conceptual distinction between interval and ratio measurement, pragmatically we use the same procedures. So for the rest of the text and these lectures, I combine interval and ratio level of measurement into a single level, and I call it the interval ratio level of measurement. Observe that almost all physical, tangible variables are at the interval ratio level. For instance, height, weight, number of cars owned. All of these are at the interval ratio level. Researchers in social science often work with multi-item scales. So as a for instance, you might have 10 questions about self-esteem, and on each of those you could respond somewhere between strongly agree and strongly disagree to indicate your degree of agreement with the statement about your self-esteem. Well, having just presented earlier the fact that averages are not valid for ordinal level variables, it is indeed the case that On multi-item scales, frequently responses are added up to form numeric totals. So we take the 4s and assign them to the strongly agrees, for instance, and a 3 to an agree, and a 2 to a disagree, and a 1 to a strongly disagree, and those point totals do get added up, and indeed we do end up with scale scores. Formally speaking, these total scale scores for multi-item scales, that is the summed scores summed up for all of the individual items comprising the scale, formally they're not at the interval ratio level, but it is the case that pragmatically most researchers treat these scales as at the interval ratio level. For the most part, we will do so in this text, and this is sort of just not all the world works in perfect ways, and I think that the consensus is that treating multi-item scales as true numeric data, as interval ratio level data, for the most part, is a good practice. So let's conclude our chapter here. It's the case that pragmatically, almost all variables that are at the nominal level or the ordinal level are categorical variables. So categorical variables and nominal and ordinal level variables are pragmatically the same thing. Rank orderings are an exception to this in the sense that rank orderings are at the ordinal level, but nevertheless are numeric rather than categorical. But for the most part, nominal and ordinal and categorical variables are one and the same. And then we've been talking about the interval ratio level of measurement, and we've also talked about numeric, which is to say quantitative variables, and pragmatically variables at the interval ratio level of measurement and numeric variables are one and the same. And that concludes our material for Chapter 1.